Hello everyone, thanks for joining today's online training. My name is Yueming Hua. I'm a senior application scientist at Bruker. So today we're going to talk about the AFM probe selection. And before start, I want to apologize. At the beginning when I set up this online session, I sent out the invitation by mistake, put everyone as panelist. So after I realized, I sent out another invitation as attendees. I think I caused a lot of confusion there. But I hope I didn't put too much stress on you, so you still enjoy the long weekend. Okay, let's start with today's topic. First, we're going to talk about the probe selection, then why we need to select the right probe, right? And the reason probably is obvious, and for certain applications, if we don't select the right probe, it certainly won't work. Like if we want to measure some electrical properties like a tuner, KPFM, if we don't select the conductive probe, it will not work. It will not give us the information we want. And even for some applications, we have multiple probes to choose. And select the right probe, it will give us best results, like for QM, right? And we need to select the right probe for the right sample, then it will give us better measurement on the modulus and adhesion, right? And so the AFM is a very important component in the AFM probe is a very important component in the whole AFM system. It's the importance is as important as other parts of the AFM, like the controller, scanners. And sometimes it's like the importance of AFM probe is underestimated. And when we select the right probe, there's a few factors we need to consider. First, we need to consider what kind of information we want to measure on the sample. Right? It could be just a simple topography, measure the roughness, measure the topography, or maybe we want to measure the conductive map. Like on the material we want to use like a tuner, right? Or we can use like a SSRM, scanning spare resistance, to measure the property. Or maybe we want to measure the mechanical property or like a magnetic property. For each different applications, each different property we want to measure, we need to select the right probe for the right application. And that's the first thing we need to consider. And also we need to consider what imaging modes we're going to use. Right? For topography, we can use contact mode, tapping mode, or pixel stacking mode. And these three different modes require the different probes to use. Right? Not every probe can work in all three different modes. And third thing we want to consider is what's the environment. Right? It could be the air, or it could be in the fluid, or in some electrical light, like for the EC, right? And this will affect our probe selection also. So there's so many probes on the market, right? Even from Bruker, there's probably hundreds of probes, and there's so many applications. How we know for certain application what a probe is the right probe, right? It makes it difficult. So, but in our nanoscope software, so for that purpose, we actually build some functions to help you select the right probe. Right? When you load the nanoscope software, right, load a certain experiment, like for example in this the piezo response, right, piezo response vertical, and there's like a short description of the experiment. And typically in that short description, there's also a recommended probe. What is the recommended probe for these applications? Right, this helps you to select the right type. And also when you go to the setup of the system, right, there's a probe setup. And there's a probe configuration. If you go to there, and it'll pop, typically there's like a recommended probe already listed there. Like for example, we recommend like a MSFRC or SMPIT for this experiment. And also if you go to the probe type, and typically those recommended probe is on the top of the list. So this list is not always the same actually. When you load a different workspace, different experiment, the sequence of the probe in the list is different. So typically we put the recommended probes on the top of the list, and this helps you to choose the right probe for the certain applications. And there's other places it helps you to select the probe, and one is like in the nanoscope help. So if you go to the nanoscope help file, there's one section, it's called probe and sample guide, and there's like a probe selection. And it has a few nice tables listed for different applications, different samples, what is the recommended probe. And in there's a little bit more details of each probe, like if this probe is good for fluid or on air only, or what's the image mode we recommend. Right? It can be used maybe tapping mode, or like contact mode, right? Or has a force curve. So this is a pretty good resource for you to choose the right probe. And when you go to our Bruker website to buy the probe, there's a very nice built-in function to help you to select the right probe also. So at the front page of the probe website, and actually there's like an easy product selector wizard, right? And for this, you can choose what application you want for the probe, and what is the mode you're gonna use: tapping mode, contact mode, people's tapping mode, or like other application advanced modes. And what AFM actually you can select what AFM you have. And in this case, I select like I want the electrical application, and the mode I want to use is the piezo response, and my AFM is icon. So then you can click search, and it will populate the recommended probes, right? And for you. Right, all these resources help you to select the right type. And sometimes you may still, after all those selections, you may still have a couple of choice of probe, right, to choose. And how can I decide what is the probe that will give me the best results? Or maybe you want to use some probe not from Bruker, right? And you still want to use it. And how can I decide if this probe is good for my application or not? And to decide that, we need to understand a little bit more on the AFM probe. So here's a diagram, a picture of a typical probe, right? There are three components for a AFM probe. There's tip, there's cantilever, and there's a substrate. And the tip is the part that actually touches the surface, imaging the surface, right? And the tip is very important. It determines what's the resolution we can get on the FM image, right? And if we can get a current or not, right? And the cantilever is important too, because cantilever basically is a sensor. It can sense the very small force by oscillating the cantilever or by the cantilever bending, right? And the substrate is just a carrier to carry the cantilever and carry the tip. And for the most of the probe, for the AFM probe, and there are two very common building materials. One is silicon, one is silicon nitride. And silicon is very easy to process. It's like most used semiconductor in semiconductor industry to make the integrated circuits. Right? It's very easy to do the micro machining, micro fabrication. It can make a very nice, very sharp, very nice tip. But it's when we use silicon to make the cantilever, it's hard to control the thickness because we need to etch the whole wafer to get that last 1 micron or 2 micron cantilever thickness. The other material is silicon nitride. It's a nice material. When we use silicon nitride to make the cantilever, typically we use deposition, and we can control the thickness of the cantilever very well. So even though silicon nitride is a very hard material, even harder than silicon, but it can be used to make a very soft cantilever. That's why typically those contact mode cantilever is made of silicon nitride. So silicon can be easily make the sharp tip, and silicon nitride can make a soft cantilever. And in most cases, the cantilever has two different shapes, right? There's two different choices. One is rectangular, one is triangular. And we think like the triangular shaped tip is more resistant to the lateral torsion. And that's important for the contact mode cantilever, because when we image in a contact mode, the tip will have some lateral force, the shear force, the friction on the surface will cause cantilever to torsion or rotate. And that's not good for the imaging. If we want to prevent that or minimize that, the triangular shaped tip is better. But if you want to, you particularly want to image those like a friction force, then probably the rectangular shaped tip is better. And when we try to choose the right cantilever, we typically look at some key parameters of the probe. right? There's for the key parameters, typically it's like related to the either tip or the cantilever, nothing much to the substrate. And some key parameters here I put, like this is the diagram of the cantilever. And the tip radius, the first one, the tip radius is very important because the tip radius determines the physical resolution we can achieve, right? And how sharp our tip, and then how the resolution we can get, how much resolution we can get. And sometimes the tip shape is also important, and cantilever shape and size is also important, especially the length. And for the like a tapping mode or contact mode, the spring constant is important. And the other key parameter is the resonant frequency. That's especially important for the tapping mode. And also for most cantilever, there's like a backside coating that increases the intensity of the laser. And the backside coating is important. And there's different backside coating we're going to talk about. And for the front side coating, typically that's for the electrical mode, make the cantilever more, the tip more conductive. And there's a couple of different front side coatings we're going to talk about. So next I will talk one by one for these parameters and how these parameters can affect our results, right? And then how we can choose the right parameter for the cantilever. So the first thing is the tip radius. So FM topography image is always a convolution of the tip shape and the sample surface structure. So if we have a sharp tip, then we can profile the surface, get a true profile of the surface. But if our cantilever, the tip is blunt, it's dull, right? The radius is too large. So, and if our sample is sharp, then instead of it's like a tip is imaging the surface, actually it's the surface features imaging our tip. Like for example, like we have the same features, right? In this diagram, same sample features, those sharp spikes. If my tip is sharp enough, its radius is small, then the tip can get into those small valleys to image the real surface. But if my tip is dull, tip radius is large, then actually the sharp spike on the surface is imaging my tip. The profile we see in the image is not our surface. It's actually our tip. So this is critical to choose the right tip radius, and in most cases we want the sharp tip radius, right? Because we want a high resolution image. Like for example, I can use the FM tip to image like the atomic lattice on some minerals like the calcite, right? I can see those lattice. Or I can use the FM tip, sharp tip, to image the DNA double helix. I can see those major and minor groove in the double helix. Right? This feature is really small. Right? For the calcite, the lattice is like a sub nanometer, right? A few angstroms. So in order to let the tip to get into those small features, we really need a very sharp tip, right? For this application, the sharp tip is important. We need to choose the as sharp as possible tip to image these samples. And typically for the tip radius, right? If it's less than 2 nanometers, that's really sharp. And if it's around 5 nanometers, I will consider it sharp also. And for most of the cantilever, for general purpose, the tip radius is around like 10 to 15 nanometers. And in some case, some tip could be like even larger, tip radius could be even larger for special purpose, like over 50 or over 100 nanometers. But for most case, right, typically we want a sharp tip to get a high resolution. But the sharp tip sometimes is not always a good choice. And one good example is to image the live cells, like the biological samples, like the live cells, right? The live cell or the other biological samples, right? It's very soft and very delicate. Like in this case, for the live cell, if we use a really sharp tip, like a 2 nanometer tip radius tip to image this live cell, the tip can easily poke through the memory of the live cell and just scratch the surface. We won't be able to get a nice image. And in this case, actually, for this nice image, live cell image, this MDCK cell, actually we need to use a relatively blunt tip. And I use like a 60 nanometer, roughly 60 nanometer tip radius tip to image this live cell. And we can see the live cell surface topography very well. And actually, in this zoom-in scan, and we can see those like a microvilla. It's called a microvilla. Those like a texture detailed texture on the live cell surface. And even though our tip is pretty blunt, it's like over 60 nanometer tip radius, but we still can get a very good image on the live cell, and we can get a very nice resolution to resolve those microvilli, right? And because the live cell, the cell is typically pretty large, like over 10 microns or even larger, right? The 2 nanometer tip is not really necessary, and if it's too sharp, it will poke through the sample. It's not good. We cannot get a stable imaging, a stable tracking on the surface. We need to use some tip that's a little bit blunt. And here, like the 60 nanometer gives us very good imaging, and also then it gives a very good resolution still to see those details on the surface. So in most cases, sharp tip is good, but in some cases, especially for the biological samples, like a live cell tissue or some soft materials, then you may need to consider use a little bit blunt tip, right? So the tip radius needs to be a little bit large. So next one is tip shape. So the tip radius is not the only thing important about the tip. Actually, sometimes the shape is also important. So in most cases, the typical the tip is like it's conical, or it's like a pyramid shape. It has the sidewall angle. And for example, like for this typical, this is a diagram for the typical tip. It has a front angle, like a back angle, and a side angle. They could be different. And when we mount the cantilever in the AFM, it has a tilt angle also. Typically, it's like a 10 degree or 12 degree. And in most cases, this angle is not that critical because the surface topography is pretty small. But when we image some topography that's very high, like a few microns, then we will see that tip shape will convolute into the profile. That's if we want to image a deep change, right? And the tip has this front angle and also to the 10 degree. And you can see one side of the profile is has a very different slope compared to the other. It's not vertical as expected. So in this case, if we want to really image this deep change or like a pit well to see a much sharper step, then we need to consider to choose the right probe, right? And one good example for this kind of feature is those fibbed cantilever, the fibbed tip, right? It has a very sharp spike at the end of the cantilever, right? It's a very high aspect ratio, and it has a much smaller angle, front, right, back, and also side. It can get into those deep change and image on those sidewalls. And for this kind of sharp spike, the fibbed cantilever, and there's another important parameter is the tilt compensation. So because when we mount the cantilever in the AFM, it's always tilt. If the spike is straight up, right, then there's always like this 12 degree or 10 degree tilt. It will still give this profile or angle on the sidewall. And in order to eliminate that angle, then some of these kind of fibbed cantilever, it has tilt compensation. It makes the spike has certain angle, right, match the cantilever tilt. So typical is like a 12 degree. So this means with this tilt compensation, when you mount the cantilever in the AFM, like it's the cantilever tilted like a 10 or 12 degree, actually the spike is straight, right? It's straight perpendicular to your surface. So you can image on the fibbed sidewall. This is something you may consider if you really want to image some very deep features. So next, let's talk about the cantilever. The first thing I want to talk about the cantilever length, right? Sometimes the cantilever length is important to get the best results for our applications. It's because the cantilever length is directly related to the cantilever sensitivity, the difference sensitivity. Right. So in the AFM, we use the cantilever, this optical lever, to detect the force or detect the cantilever movement. And in this optical lever, so when our cantilever is bent, the vertical diffraction changes on the photodetector, and it's this angular movement of the cantilever. Actually, the angular movement of the cantilever is causing this diffraction change. The vertical movement of the cantilever, right, in the vertical in the z direction, it's very minimal. It's a few nanometers, right? And it's mainly because of the angular movement. And when we have a longer cantilever, the same amount of the bending in the z direction, like the z nanometer, it generates a smaller angle. But if the cantilever is shorter, it will generate a more angular movement, and that will create a more deflection signal in voltage. And that means the short cantilever will have better deflection sensitivity, right? Typically, we have deflection sensitivity in nanometer per volt. This value is proportional to the length, but the smaller this value means the cantilever is more sensitive, has better sensitivity. And this cantilever deflection sensitivity could be very critical in some of the applications, like for the piezo response microscopy, like AFM, or like in atomic resolution. And first, I'll give you an example for the piezo response mode. So in the PFM, right, we use the cantilever in contact mode, in contact with surface, then apply the AC bias to the tip or to the sample to cause the cantilever, the sample to contract or expand. Right, the sample, this movement is very small, probably in picometer range. Right, and of course our tip needs to be conductive in this case. But in order to detect those like a picometer movement of the sample, like in the vertical, right, especially, we need the cantilever needs to be really sensitive. Right, we need to have very good sensitivity of the cantilever to detect that small amount of the small change in the sample size in the vertical. Right, and we have like a typical recommend like a SCM PIT probe or DDSP probe. Right, and the big difference between these is the length. Right, PIT probe has like a nominal length is 225, and the DSP about a half, right, 125. Right. So here the spring constant is not a big key parameters here. The length is more important. Right, with the SCM PIT, right, we image on the sample surface. This is our standard sample. This is the PPN sample, and we can see this contrast between different domains, right? These two different areas have different polarity, and we have a certain amount of contrast, and you can see a little bit of noise, right? And when I use the TDSP, right, a short cantilever, scan on the same area, you can see this area is about the same, right? I have a much better contrast. So every other setting is the same. So the actual sample movement up and down is the same amount over the picometer, right? But with the DDSP, I have much better contrast, much better sensitivity, right, on this sample. So in this case, the difference made by DDSP is its length is shorter compared to the SCM PIT. The other good example for the cantilever length important is the atomic resolution. Right? In the atomic resolution imaging, we want to use the cantilever to detect those small topography change in the lattice. Right? Inch is like the cell, like the repeating structure of the lattice. The topography change is very small, probably around like 50 or like 30 picometers. How we can detect that small topography change? And then we can feed back correctly to image the lattice. Then our cantilever deflection sensitivity is very important. So we need to use a very short cantilever for this kind of applications, because short cantilever has a good, better deflection sensitivity. Right? Typically, like I use the FastScan-C probe, right, for this kind of application to image the lattice, the atomic resolution in the typical tapping mode. And the FastScan-C is a really small cantilever. Right, it has the length is only 40 microns length, and it has different sensitivity. The nominal is like 12 nanometer per volt. That's really good. Right, and the FastScan-C you can use not only on FastScan, you can use on ICON multimode. They all work. Right, the second choice probe I use is like the Scanasys Fluid Plus. It's a sharp probe, but it has a little bit longer length, like a 70 micron length. And defense sensitivity is slightly worse than FastScan-C, like a 22 nanometer per volt. I can get atomic resolution with the Scanasys Fluid Plus, but it's a little bit more difficult. And the other choice is SNLC probe. right? It's a very small cantilever also, and it's like a very popular cantilever we use for the fluid imaging, the high resolution fluid imaging. But this cantilever has 120 micron length, and differential sensitivity is about 30 nanometers per volt in the fluid on icon. And I need to try hard to use this probe to get atomic resolution on calcite. So it's not that easy. So the main difference between these three cantilever in terms of the performance on atomic resolution is not their spring constant, right? It's because of their length. FastScan C is much shorter, 40 micron. The scanner's fluid plus is 70. Scanner's SNLC is 120. So the short one is better. Actually, the FastScan C is the 0.8 Newton per meter is the most stiff one among these three, but it can have the best performance in atomic resolution imaging for this kind of hard sample. So next one is cantilever shape. So the length is part of the shape, but there's other part of the shape of cantilever shape is also important, especially in fluid imaging. Right? In the fluid imaging, our environment is like the liquid water or other aqueous solution. It has more damping to the cantilever than in air. It's significantly higher, right? And to operate well, like especially for the tapping mode and the people's tapping mode, and the cantilever need to be the shape is important. Need to be narrower and shorter, right? Again, like the SNL probe is very popular for the fluid imaging. There's 4 cantilevers on the probe. There's like two on the one side and 2 on the other side. Like this, the top 2 is the thicker, and there's a bigger one and a smaller one, and the bottom 2 is the thinner. The cantilever leg is narrower, and one big one, and smaller one also. And if we want to use SNLC in the tapping mode or in people's tapping in fluid, and probably you already know, we typically use the C. And what is the reason here? The C is the smaller one, and the leg is narrower, so it has less dampening in the fluid. The shape is the cross section of the shape is smaller, so it has less dampening in the fluid, so it can operate in the tapping mode or people's tapping mode, right? And that's important. So this is why the cantilever shape is important in fluid imaging, right? And actually, like for further reduce the dampening of the cantilever in the fluid, like we can further reduce the cross section of the area. And one good example is the FastScan D probe. I'm not sure if you use this one already. So this is a very nice probe, right? It's designed for the FastScan. So it has a very smaller cantilever, much smaller, and it has this kind of we call like an ice cream bar shape, right? We have the cantilever, the head is a little bigger, so we can align the laser on it. The cantilever is much narrower, much shorter. This significantly reduces the dampening in the fluid. So it has much higher resonant frequency in the fluid. It can scan faster. Right. So next one key parameter we talk about is the spring constant. I think this is one of the most important parameters for the probe, for the cantilever. And when we choose the spring constant, like for the contact mode, so we need to use a low spring constant because it has the better force control. We can control the force lower, right? And for the tapping mode, typically we want the cantilever spring constant like a medium or higher because it prevents the tip to stuck in the surface when there's like the adhesion force. If you stuck, it will cause noise in the feedback, and it's not good for the imaging. So typically for the tapping mode, it's the cantilever is relatively stiff, right? The medium or high, and the spring constant typically like 2 to 100 nanonewton per meter. For the contact mode, typically less than 1 newton per meter. And sometimes for some biological sample, for the contact mode cantilever, for the biological sample, it could be like less than 0.1 Newton per meter. It's really soft. And for the tapping mode, sometimes we want to see the face imaging, and for the face imaging, we want to use the medium spring constant. Right? And I will talk a little bit more about that. And also, like the spring constant is also a big key parameter for the people's tapping mode, because in the people's tapping mode, especially for the QM, we want to match the spring constant of the cantilever to the modulus of the material, so we can get a better measurement of the modulus. And if you're already using QM, I believe you already know how to choose the right spring constant for the QM. But I will slightly more detail on the third item, like how we can choose the right spring constant for the phase imaging for the tapping mode. First, let's take a look at the tapping phase. So in the tapping mode, we drive cantilever with sinusoidal drive signal, right? There's like it's a sine wave. It has a phase angle, and the cantilever will respond, will oscillate, and generate a sinusoidal response signal from photodetector also. And when we compare these two signals, right, there's a phase difference, phase angle difference. That's our tapping phase, right? And this tapping phase could be related to the sample mechanical property, like if it's soft or if it's sticky, it will give the tapping phase contrast. And it could be also like the magnetic force, right? If there's like the sample, like the flop disk or the hard disk, there's different magnetic domains and have different magnetic force. It will also interact with the tip and cause the phase to shift. And the magnetic force phase is the key data channel for the MFM, right? And that's tapping phase also. And another example is for the phase, right? And also for the material property, like we talked about already. And also for the KPFM, right? There's a phase also. We need to feedback on the phase for the frequency modulation. So the phase is important, and what causes the phase to change? Why this induction can cause the cantilever oscillation phase to change, the tapping phase to change? So we can take a look at this model of the cantilever, right? The force, the induction force between that tip sample could be the mechanical force, like a tip is cantilever is soft or stick, the sample is soft and sticky. That's a induction force between tip and sample. And it could be the electrical force, and it could be magnetic force. And this force will generate a additional spring constant and cause the cantilever resonance frequency to shift. And the amount of the resonance frequency can shift is proportional, inverse proportional to the square root of the spring constant, right? I put the equation here. So this partial S, partial Z, that's basically the interaction force between tip and sample. Could be like the atomic force, could be electrical force, could be magnetic force, right? We have a certain amount of interaction force. But if we use softer cantilever, if the spring constant is softer, right, this same amount of interaction force can cause a larger frequency shift, right? So the soft cantilever gives more frequency shift. And we know, if we look at the tuning curve of the cantilever, right, the tuning curve shift, the resonance frequency shift actually is the root cause of the phase change, right? When the resonance frequency shift, right, the phase curve, the shifts also, and the intersection point between our drive frequency and the phase curve change. And this change, delta in the vertical in the phase, that's the phase, tapping phase change, right? And if there's a different material, have different interaction, then it will give this contrast, right? So more frequency shift will give a better contrast in the phase, right? And we know soft cantilever gives more frequency shift with the same amount of the interaction force between tip and sample. Doesn't matter if it's atomic force or like a magnetic force or the electrical force, right? Then we can take a look at this two cantilevers. I use these two cantilevers as example, right? If I want to get the good phase contrast on some sample, right? I have two cantilevers can choose. Like for example, I have like 10 test for 300, right? The spring constant is typically around 42 Newton per meter. That's nominal, right? I have another choice. Let's say I have like an test for 150, right? So the resonance frequency is about 150. So 300 resonance frequency is about like 300. So the test for 150 has spring constant about 5 Newton per meter. So much softer, right? And if we look at the phase, the tuning curve, phase versus frequency, right? They have similar slope. So you can see the scale for both cantilever is the same. For both the vertical is the phase degree, and the lateral is frequency. And each dividend in the frequency is like 0.5 kilohertz, right? The slope is similar. So this means like if I shift the frequency more, then I'll give a better contrast in the phase, right? So for this, like a 40 Newton per meter, 40 Newton per meter, and the 5 Newton per meter spring constant, right? Their slope of the phase is similar, but the spring constant is very different. And in this case, the RTSPA 150, I would say, is almost 3 times more sensitive on the phase compared to the RTSPA 300, right? Because the spring constant is much softer, it's much lower. And here I'll show you a good example. So this is a block copolymer, right? In this case, I need to use the RTSPA 150, and it's very easy. I can just set up the tapping mode, and I can get a very nice phase contrast in this block copolymer. But I can also try to use RTSPA 300, but I tried, so it will be much more difficult. And even I get the phase contrast, it will be much smaller. So it's not that I cannot get the phase contrast with other tapping probe, but it will be difficult, and the data is not as good. But if we choose the correct probe, like an RTSPA 150, it makes much easier to get a better contrast, and the contrast is much better also. And in this case, the spring constant is very important. And that's why if you look at those probe for the MFM, for the EFM, or for the like a KPFM, right? All those probe are soft tapping mode probe. The spring constant is probably like a few Newton per meter. They never use very stiff cantilever for those applications. Because in those applications, we want to detect the phase. And the medium soft cantilever, tapping mode cantilever, is the best for the phase sensitivity. And same thing for the tapping mode phase here, right? We use the TAP 150 or like the RTSPA 150, gives a much better results compared to the RTSPA 300. So next one, I want to talk about the resonant frequency, and this is the key parameter for us when we choose the tapping mode cantilever, right? So the resonant frequency is a determining factor for the response time. And here I put a cantilever response time here, so it's proportional to the Q and inverse proportional to the resonant frequency, basically the Q over the resonant frequency. And typically we can control the Q by designing the cantilever shape, right? So this is like a fast scan, we use like a closed triangle shape, so we reduce the Q, so it has, so it's not, it's like the Q is very similar to regular tapping mode. I think both cantilever for like the RTSPA 300 and the fast scan A probe, those are tapping mode probe, has a Q around like a 300 to 500, very similar. But the difference is like the resonant frequency. The fast scan A probe is the frequency, resonant frequency is much higher. It's 1.4 megahertz. Right? For the typical RTSPA is around 300 kilohertz. So almost like 5 times higher. That means the response time is 5 times smaller. They have I just mentioned they have a similar Q here, right? It's 5 times smaller. That means the fast scan A probe can scan 5 times faster, right? At least 5 times faster than the regular RTSPA probe. And this resonant frequency is important. So if you have a fast scan, right, already can scan faster, then in order to really scan faster, you need to choose the fast scan A probe, right? If you put an RTSPA 300, right, the regular tapping mode cantilever on the fast scan, it can operate the tapping mode, but it cannot scan as fast as you combine the fast scan A probe with the fast scan. Next one, I'll talk about the backside coding. So the backside coding is it helps to increase the laser signal. Typically, we recommend to use the backside coding if possible, right? Because it increases the laser signal. It has a better signal. You can reduce the noise in the image. Right? This is a good thing. But sometimes the backside coding could cause some problem, right? Because the backside coding typically we use metal, aluminum, or gold, right? The different material compared to the cantilever material, like a silicon or silicon nitride. And this will cause called like a bimetal effect. So if the cantilever temperature change, it will cause the cantilever bending, right, automatically by this bimetal effect. And this could be a problem if you use, if you want to use on the heating cooling stage, right? Because your sample temperature is changing, and it will cause the cantilever temperature to change also, and it will cause like additional bending in the cantilever, and this will cause a problem in the imaging and tracking the surface. And for those cases, you can consider use some probe without a coating. Actually, there's for some of the probe, there's a version like that without a coating that helps to reduce this bimetal like bending effect. But one thing I want to mention here, right? And for the coating, backside coating, typically we have aluminum or gold, and they designed a different purpose, right? For the aluminum, it's typically using air, and the gold is in fluid. And in the fluid, sometimes you may use like some chemicals, right? Some has different pH or a little bit of corrosive, and the aluminum is not a good choice because aluminum is a relative active material. If you have some acid, right, it can dissolve this aluminum, and if you use this probe with aluminum coating in the EC, right, very likely you're going to dissolve the coating on the aluminum, and you will see a transparent cantilever actually. So in those cases, you need to use the cantilever coated with backside coating with the gold. It's more inert, right? And you can see in those on our probe website. Look at those like cantilever designed for the full imaging, right? All those cantilever is coated with gold, not aluminum. So next time if you try to use some probe designed for the air, like has the aluminum backside coating in the fluid, then you might need to reconsider, choose some cantilever differently. A similar cantilever but with gold coating. And the other one is the front side coating. Right? Typically, we put a front side coating to make the cantilever, the probe more conductive for electrical measurement, like for the tuner or like for SSIM to make the connection, the actual connection with the sample. And there are a few common front side coatings. Right? The most popular one is platinum iridium. It's a very hard alloy, so it's a good coating. It makes the tip really conductive. Right? And typically with the coating, the tip radius will be a little bit larger because we are adding on another layer to the tip. The other coating we can use is like a platinum silicide. This is kind of a little bit newer coating we use for conductive probe. And the good thing about this the platinum silicide, it's very conductive, but it's also very hard material. It's much harder compared to the platinum iridium. Even though platinum iridium is a hard alloy, but it's still a metal, right? Typically metal is not that hard, but a platinum silicide kind of ceramic, so it's much harder compared to the platinum iridium. And also it gives a little bit a smaller tip radius. So if you want to do some electrical measurement, especially for the tuner or the KPFM, so you maybe need to consider this a platinum silicide coated probe. One good example is the PTSI probe. So we found this probe is, I think the performance is better compared to the PIT probe in terms of the resolution, like in the tuner in the KPFM. Right? And the other popular coating is conductive diamond. Right? One good example is the DDSP. Right? But with this diamond coating, the tip radius is much larger. But since it's diamond, it's much harder, even harder than platinum silicide. Right? For some application, if you especially for the SSIM, typically we want to scratch into the surface. Right? For semiconductors, typically there's a native oxide on the surface. We need to penetrate through that oxide layer. Right, we need to tip the material much harder. So the DDSP then is a good choice for the application. Right, we need to select this DDSP as our probe for the SSIM typically. right? But of course, there's a downside. The tip radius is much larger. But in the SSIM, the tip radius is not a control factor for the resolution. Actually, it's a counterpoint. So, but if you are considering for using TDSP for the other application like the tuner or the KPFM, then it's not a good choice because the tip radius is much larger. It doesn't give us other better benefit compared to the city side or the platinum city side or the platinum irradiant tip, right? So for different application, we need to choose the probe have the different coatings. Okay, I think that's all about our probe. And to finishing today's session, I just listed the common used probe for different modes, like scannesis, those basic imaging modes, and some application modes, right? And we have some time, and I can take some questions if you have. Let me take a look. There's some chat. Audio has cut off. I'm not sure if that's a problem. I think sounds like it's good from my colleague. It sounds like the audio is good. So, but if you missed some part, I have the recording this online session. So after this, I will convert to the video and upload it to the website. Let me take a look if there's a question here. So I have a question here. It says, do harder front side tip coating such as conductive platinum silicide and conductive diamond helps resolve conductive coating so that lasts longer when staying in contact with contact mode? Right? I noticed my tip coating very quickly come off, cause the loss of conduction. Right? That's the exact same the purpose of our for us to put those hard coatings like a conductive diamond or the platinum silicide compared to the platinum iridium. But one thing, when you do the conductive measurement, like you say, the coating come off. One thing I want to mention that is make sure the current is not too high, right? One common problem in those conductive measurements is the sample is maybe too conductive, and the resistance between tip sample is very small. And if you apply a few hundred millivolts or 1 volt, it can cause a huge current going through the tip and the sample, and that current is all concentrated into the contact point, the tip, and it can melt the coating immediately. Doesn't matter if it's platinum silicide or diamond, like a doped diamond, right? It will melt those coatings easily. And that could be a problem. So make sure it's not a problem. Yeah. And another thing is you may consider if your sample is the soft, if there's some contamination, right? Because those hard coating, if you really operate in contact mode, it can scratch the surface. And if the surface can easily get scratched, maybe the debris you look at is not the coating, it could be your sample. The debris from sample. Question. I think that's the only question I had. So thanks for attending. That's what to do.